Hello friends, welcome to our channel. In previous videos, we discussed about continuous function in a metric space with some properties of closed and open metric spaces. Now, in today's video, we will discuss uniform continuity and isometric in a metric space. Uniform continuity. Let xd and yd star are any two metric spaces and f is a function from x to y, then f is said to be uniform continuous if for given epsilon greater than 0 there exists delta greater than 0 depending on epsilon alone such that distance between x1 x2 is less than delta. This implies d star f of x1 f of x2 is less than epsilon for every x1 x2 belongs to capital X. By definition of uniform continuity, we see that every uniform continuous function is always continuous function but continuous function need not be uniform continuous. We shall show by example that every continuous function need not be a uniform continuous, but uniform continuous is always continuous function. Example, prove that the function f r to r such that fx is equal to x square for all x belongs to R is not uniform continuous function. Solution: let f r to r is a function defined as fx is equal to x square, where R is a usual metric space as fx is equal to x square is a polynomial function and we know that polynomial function is always continuous function everywhere. Therefore, fx is equal to x square is a continuous function we shall prove that fx is equal to x square is not uniform continuous function. Let epsilon greater than 0 be given. We claim that there is no delta greater than 0 such that distance between x and a is less than delta. This implies distance between f of x and f of a is less than epsilon for every x and a belongs to R. If possible, let us assume that delta greater than 0 exists. Take belongs to R such that A is greater than epsilon by delta, and let x is equal to A plus delta by 2. Then A and x both are belongs to R. Now distance between x and A is equal to modulus of x minus A is equal to A plus delta by 2 minus A, its modulus, which is equal to delta by 2, which is less than delta. And distance between f of x and f of A is equal to modulus of x square minus A square, which is equal to modulus of A plus delta by 2, its square minus A square. This implies distance between f of x and f of A is equal to A square plus delta square by 4 plus A delta minus A square, its modulus, which is equal to delta square by 4 plus A delta, its modulus, which is greater than A delta, because delta square by 4 is greater than 0. Which is equal to epsilon. Thus, distance between x and A is less than delta. This implies distance between f of x, f of A is greater than epsilon. This implies f is not uniform continuous. So every continuous function need not be uniform continuous function. Next example. Show that the function f from 0, 1 to R defined as f of x is equal to x square is uniform continuous function. Solution: let f is a function from 0, 1 to R defined by fx is equal to x square. Let epsilon greater than 0 be given and x1 x2 belongs to 0 1. Let delta is equal to epsilon by 2 is greater than 0. Then distance between x1 x2 is equal to modulus of x1 minus x2 is less than delta. This implies distance between fx1 fx2 is equal to modulus of x1 square minus x2 square, which is equal to x1 plus x2 into x1 minus x2 its modulus. This implies distance between fx1 fx2 is equal to x1 plus x2 modulus into x1 minus x2 modulus, which is less than equal to x1 modulus plus x2 modulus into x1 minus x2 modulus, which is less than equal to 2 into x1 minus x2, because x1 modulus is less than equal to 1 and x2 modulus is also less than equal to 1, as x1 x2 belongs to 0 1, which is less than 2 into epsilon by 2 is equal to epsilon. Thus, if distance between x1 x2 is less than delta, this implies distance between fx1 fx2 is less than epsilon. Thus, fx is equal to x square is uniform continuous function. Next theorem. Let XD be a metric space and let capital A be a non-empty subset of capital X, then the function f x to r defined as fx is equal to distance between x and a is uniform continuous function. Proof: let xd be any metric space with metric d. And capital A be any subset of capital X. Let epsilon greater than 0 be given and delta is greater than 0, so that distance between x and a is less than delta for every x and a belongs to capital X. Now f of x minus f of a, its modulus, is equal to modulus of distance between x and capital A minus distance between small a and capital A modulus, which is less than equal to distance between x and a, which is less than delta, is equal to epsilon. Thus, if distance between x and a is less than delta, this implies distance between f of x and f of a is less than epsilon. This implies f is a uniform continuous function. Next, isometry. Let xd and yd star are any two metric spaces, then a function f from capital X to y is said to be isometry if distance between x and y is equal to d star f of x and f of y, that is distance between fx and fy, for every x y belongs to capital X. These two metric spaces xd and yd star are called isometric spaces. Example, prove that an isometry is a uniform continuous function. Solution, let x d and y d star are any two metric spaces and f x to y is an isometry, we have to prove that f is uniform continuous function. Let epsilon greater than 0 be given. Suppose delta greater than 0 such that delta is equal to epsilon and distance between x1 x2 is less than delta for every x1 x2 belongs to capital X. Consider distance between f of x1 f of x2 which is equal to distance between x1 and x2 because f is isometry which is less than delta is equal to epsilon. Thus dx1 x2 is less than delta. This implies d star fx1 fx2 is less than epsilon. This implies f is uniform continuous. Contraction mapping. What do you mean by contraction mapping? Let XD be a metric space and YD star be another metric space f x to y be a function then F is said to be contraction mapping if D star f of x f of y is less than equal to alpha into dxy for every x y belongs to capital X and alpha is greater than 0 less than 1. Then this mapping is said to be a contraction mapping. Next theorem. Prove that every contraction mapping is uniform continuous on metric space X. Proof. Let XD be any metric space and fx to x is a contraction mapping let epsilon greater than 0 be given and delta greater than 0 such that delta is equal to epsilon divided by alpha. Let dxy is less than delta for every xy belongs to capital X. D of f of x f of y is less than equal to alpha into dxy because f is contraction mapping which is less than alpha into epsilon by alpha which is equal to epsilon. Thus, if distance between x and y is less than delta, this implies distance between f of x, f of y is less than epsilon. Hence, f is uniform continuous on x. It is sufficient for today's. In the next videos, we will discuss some more topics related to metric space. So keep in touch, watch our videos and subscribe our channel for more videos. Thanks to all. Have a nice day. Bye bye.